Could be the start of like fame and fortune, you never know. All right, yes?
How many numbers can fit on it, like storage?
Quite a few. I don't know how big the heap is, but at least hundreds of megabytes, I believe.
Follow-up question, what's that heap?
The heap is a structure where memory is stored, sort of. It's the thing that Malik goes to when you ask for memory. It pulls it out of a heap. We're going to talk about a data structure called a heap next term, and it's a different kind of heap. But just think of it as a big pile of memory waiting to be used. And when you say malloc, it goes into the heap and it finds a chunk of memory and hands it to you. And when you say free, it takes that memory and throws it back in the heap. If too many mallocs are done, then you'll run out of storage in the heap and you'll get an error from malloc.
So is it called a heap because it's relatively unorganized?
I think so. I don't know how it relates to a heap storage, which we'll talk about next term, but I don't know the etymology of that term. But that's how I picture it, as just kind of a pile of memory locations.
So does malloc return null if nothing's out?
If it can't find enough memory to allocate, it'll return null. And that's your warning that you're out of heap space. So with Java, for example, when you run a Java program, you can say how much memory, how much heap you want the virtual machine to have. And there's a default, but you can bump it up. And I think it's technically limited by how much virtual memory you have, which is the size of your disk, theoretically. So it's pretty hard to run out of it unless you have something going crazy. You just allocate it. All right, other questions? Parting comments on PA2. So let me run through an example. I'm going to pick on someone's code, but I've taken out their names, so if they don't want to out themselves, that's fine. But a lot of people were having issues with memory leaks, right? Memory leaks are kind of notoriously difficult to track down.
All right, I'd like to say something.
Mm-hmm.
For anybody else who uses printf statements to debug, make sure to always put a new line in because the segfault message overwrites any output.
Right. So yeah, that's a good general debugging when you print. Remember, we use buffered output, right? The system's trying to be efficient. So if you print something without a new line at the end, it doesn't print immediately. Okay, it prints when you're asked to print out a new line, or if you do something that's getting input like an fgets, that will force whatever's been buffered in the output to actually appear. Or you can say flush, standard out, and it'll force all of this. But if you just say print, you don't have a new line, this is sitting in the output buffer. And if before it appears you get something like a segfault, you get the segfault message and this never appears. And yeah, that can really mess you up debugging because it actually got to this point, but you didn't notice because it didn't flush. So thanks for bringing that up. So memory leaks. Let's see. So let me run this PA2. And Valgrind gives me a message in the beginning, first of all, which we'll talk about shortly. But I can insert some numbers. I can print them out. Oh yeah.
Yeah.
All right, so I can insert numbers, I can print them out, and then when I exit, I get a message from Valgrind saying in use at exit 64 bytes, 48 definitely lost, 16 indirectly lost. So there's memory leaks somewhere in this program. So how do you find it? Here's one suggestion. So you're calling malloc to allocate memory, you're calling free to free memory. So let's wrap those around our own code. So here's what I'm going to do. I'm going to change all of the calls to malloc to be calls to my malloc. So new equals my malloc such and such. And all the calls to free will become calls to my free. And now I'm going to write my own versions of malloc and free. So malloc's supposed to return a pointer. I'm going to do a void star because it'll suppress some warnings, but you can do a car star or anything else, it doesn't matter. So my malloc, and it takes an integer argument. And I'm going to print out what it mallocs. So let's do a void temporary temp equals malloc, and yeah.
That's fine by the way there.
Okay. So I'm going to call malloc, right, the real malloc. I'm going to ask for n bytes. I'm going to take the value it returns. I'm going to restore that in temp. And before I return that, I'm going to print it out. And %p works well. %x will also work. But let's print out the address that was malloc. And then let's just return temp. So now I have my own version of malloc with this extra feature that after it allocates memory, it will print out a message saying malloc, and it will show me the address that it allocated. And I'm going to make a version of free also, for free doesn't return anything, but it takes a pointer as an argument. And I'm going to print a message that shows me the value of the pointer, and then I'll free my pointer, and I'll return. It's not like I got my own memory allocation and release routines, but they're giving me informational messages. So I'm going to compile this. I spelled something wrong.
I think you named your function free.
I did. All right, and let's run this. So the first thing I notice is it allocated some memory right in the very beginning, which is probably the Sentinel node. So I can insert 10. And it did 2 mallocs. I can insert 20, it does another 2 mallocs. And when I exit, it does 1 free, which was the original node. So the Sentinel got released, but not those other nodes. And I know this is a later version of some other attempts that were made. So let's try the delete function. So let's insert 10. So I malloc locations 10 in the very beginning for the Sentinel, and then 50 and 70 to store my 10. If I delete the 10, it frees the 70, but not the 50. And now when I exit, it will tell me I have a leak. It freed the Sentinel. Well, I didn't run Valgrind, but it would tell me I had a leak because that 50 is still allocated and not freed. So you can run this on whatever test case you have that's generating Valgrind errors and see each time that you allocate and each time that you free. So go through those and pair off each malloc with each free and see which ones are not paired. And that's where you did a malloc that you didn't free. If that doesn't tell you where the problem is, start putting in some more print statements. So don't just say malloc, but actually say, inside my search routine, inside my delete routine, so that you know where these mallocs are happening, and then go into your code and find it. So this double malloc seems to be happening inside the insert. So go down to the add routine. And right here is a call to get node. And if you come further down, there's another call to get node. So this first call is being done to make sure you have space available. But when you call get node, it allocates space for a node. And nothing's being done with the return value, so you have no access to that node, so you can't free it. So that's where the memory leak's coming from in this case.
So how do you search for like different parts of the program using regular expressions?
Oh, I just did something like $1, substitute malloc, my malloc, go.
No, just search different words. Like you search to go down the list to the next.
What do you mean?
Just slash.
Oh, to search for something, yeah, just slash.
So I did where up there where it says struct node and then the pointer to new node. I set that equal to get node.
Okay,
And then remove the new node equal get node out of the other parts of the function.
okay.
And then where it says, let's see, where is it? The first part where it says get node equals null, and set it to new node equals null.
So you got rid of this.
Well, I left it, but I changed it. I changed instead of get node, it just said new node.
Okay. All right.
And then, there's 2 times where it says new node equals get node. I just deleted those lines. Because they're not needed anymore.
Okay. What do you have here?
Go up there.
So does that work with Valgrind?
Yeah,
Cool.
so everything works now.
Okay, cool.
And it's a lot cleaner too.
So there's 1 node for 10, there's 1 node for 20. We've got a total of 3 nodes allocated. If you delete 10, it deletes that. If you delete 20, it deletes that. And when you exit, it frees the sentinel. Right, no leaks.
And it fixed that message you were getting under the menu too, where it said there's a jump.
Right, so you have this message up here in the beginning. Conditional jumper move depends on blah, 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 blah. PA2.C72. So,
In my main, my one was conditional to something that hadn't been initialized, so I set it to a random number. I put 42
Cool.
in or something like that.
yeah, so we can debug, we can say GDB PA2, and it's telling us the error was at line 72, so we can just say break 72, run. And this is the instruction that's about to execute and generate that message. Or we're comparing command to X.
And command.
If you print command, it's got stuff in it. So then you go look at the code and you realize command wasn't initialized, and that's all it's complaining about. So Valgrind, GDB, print statements, rewriting, wrappers around memory routines, things like that, all potentially useful debugging tricks. I tried Valgrinding GDB and that was a nightmare. It like really freaks out. Kind of thinks for a long time, then it goes, wah. There's something in GDB it doesn't like. Yeah, 1,400 errors. All right, so I just wanted to run through that. That's just an example of trying to tackle these memory issues.
So the memory check or like the memory error before the program actually prints off the statement, what is that? Like on Valgrind, it shows an error message usually.
This one?
No, before it gets printed.
saying I'm memcheck, a memory error detector, copyright. Yeah, it's
Yeah,
just
that's
information. It's a chatty program. And what is the 3626?
The program number or just process number?
Guessing it's a process number. So I'm at 3658, so yeah, that's the process ID number. All right, so on to PA3. Which I'm not going to read the canvas, that's always slightly annoying. Somebody just look at the PDF. This is another 4-page description that I intended to be simple, but it got more and more complex. So I'm going to put a general disclaimer here. If you're not sure what some of this is saying or what you're supposed to do or what's expected, just ask. Because I don't want to make this long enough to cover every possible question, because it'll be, you know, the assignment from. So, so I tried to stick to the highlights. So you're writing a hash function. You're implementing a hash table using a set of functions. And two things to know up front. Number one, this is a group assignment. So I will let you work in groups of 2, or you can work alone. No groups bigger than 2 though. And being a group assignment, you can work with the person in your group, you can work on the code together, you can talk about it and so on. But I still don't want people from one group talking to other people from another group about their code in particular. You can talk about generalities, you can kick around ideas, I'm stuck with this, what did you do? But don't look at other people's code, okay, other than the person you're working with in a group. Does that make sense? All right, so that's the first thing, it's a group assignment. Second thing, I will give you a main program, okay, kind of like the one-day program, because I'm giving you source code for the main program. You're writing the functions to implement a hash table. You should write your own main programs as you're writing your functions to test them as you go. The main program I'm giving you is a couple of 100 lines of C, and it's pretty dense. And you don't want to use it to debug, because there's a lot going on in there. But if you write your functions and you've tested them with your own main programs and they work, you should be able to link them into the program I'm giving you and have a fully functioning database program. Okay? But be prepared to write your own main programs to test stuff as you're going. But when you're done, you can link into the program I'm supplying you, and it should all work. So let me show you what that looks like. So here's the main program. It basically gives you a menu of options. You can add data, search for data, delete data, print all the data, or exit the program. Okay, so let's add some data. We will ask you for a name, so we can put in Izad, and it will ask you for why they're famous. So, wrote a lot of books. Year of birth. I don't know how old Izad is, so I'll just go. And is Izad still alive? Yes.
Maybe.
Maybe.
We don't know.
All right. And if he's not alive, it'll ask you for a date of death. So I can say search for Nick, and Nick's not found. I can say search for Izad, and there's Izad's information. Okay, so let's add Nick. Why are they famous? Wrote this program. Go back to Steam era, and yes, I'm still alive. All right, so now I can search for Nick, and type in the name Nick, so there's Nick's information.
What does it look like when you print?
So print just goes through and it shows you all the information in there. So there's Nick, there's Izad.
Here lies Nick, 1850, 50, wrote that one database program.
Yeah. That's all I did after 150 some years.
So the next key function is something that you would be using to go through for the print statements.
Yeah, so I'll show you the code. All right, so you got the basic idea. Anything it doesn't know, it just shows the usage. So basically add, search, delete. So I can delete Nick from the database, it says success. If I delete Nick again, it's going to fail because Nick's not in there. If I delete someone random, it's going to fail. If I print, he's the only one in there, and so on. So what I've done for myself was I made a file, I called it Go, with a whole bunch of commands for driving my program. So add Izad as a great teacher, add Nick as a program, add CJ as a famous dog, and so on. And I'm just going to select all of this. And now I can just right click and it does all of those things. And now if I print, I've got all this stuff in my database. So you can make yourself test cases, right? Throw a bunch of commands in a file, and then when you want to test your program, you can simulate commands like this. And again, you're probably going to be testing on your own main program, whether that is. All right, and X takes you out. And if I do all of this, I put all of these people in, then I X out. This should free everything. And I set it up so that if you Control D out, it does not free memory. So if I just Control D, it'll show me all my memory that was in use. And it's a whole lot of allocations. All right, that's the high-level behavior of the program. Let's talk about details of this, and then I'll go back and I'll show you the source code for main as an example of how you can call these functions that you're writing. All right, so first thing, you're building a hash. We're going to use a hash that's got 101 cells to it, so an array of length 101, but use the symbol hash size. Okay, I'm going to give you a .h file. It'll define hash size to be 101. Don't put 101 anywhere in your code, okay, unless it's in a main program that's testing something. All the functions you write should use hash size, so that if you want to make a hash with a different size, change that one define in the .h file and just say make. You've got a new hash function set. So the hash entries look like what we described yesterday on the board. 4 pieces. There's a key, there's a value, there's an in-use flag, and there's a deleted flag. All right. I've typedefed a few things to simplify the way this code looks. So a pointer to a struct hash entry is just called a hash. So you can say hash space T, and T will be a pointer to a struct hash entry, which is your hash table. Okay, we'll see this in the code shortly. So a hash is just a struct hash entry star. Key is typedef to a char star, because your key is just a string. Value is typedef to a pointer to struct data, because the information you're storing in this table associated to each key is complex. It's got a reason why the person's famous, it's got a birth date, and it's got a year they died. It's got 3 fields to it. That 3-field collection is called a struct data. And so value is a pointer to struct data. So when I say hash entry has a value of type value, right, this little case value is just a pointer to a struct data. And struct data is year of birth, year of death, or a 0 if they're still alive, and then a character string for why they're famous. So again, this is going to give you a lot of practice at working with structures and getting more experience with thinking in terms of structures, right? We work with integers and characters and doubles, but we'd like to be able to work with a struct data and be able to take that thing and say, okay, this is what this struct data is. And in 223, when we're doing object-oriented programming, that's the whole name of the game. right? We're just going to, everything's an object in Java. It's a thing like a struct. And so we want to get comfortable with sort of thinking in that kind of mindset. All right, your hash function is the same as ODP 10. So 7 plus the weighted sum of the ASCII codes multiplied by the square of the probe number, reduced modulo 101. And you call that function the same thing, hash. It takes a key, which I type as a key, but it's really just a car star, and it takes an integer probe.
So that modulo 101 should be hash size.
Mm-hmm. Exactly. Mm-hmm.
So our hash function from ODP10, we actually wouldn't even have to change the car star like buffer, right?
Right.
Because-
It is a car star, yeah.
Because it's technical. Okay.
Yeah, and if you call it a car star or you call it a key, it will compile exactly the same.
Okay.
Yeah. The only thing is change 101 to a hash size. All right, so here's the functions that you need to write. First, an initialize your hash function, okay, which is ODP10. You need to write an initialize routine. It takes no argument and it returns a pointer to an empty hash table. So it has to allocate space for hash size entries, where each entry is a struct hash entry. It's got to clear the in-use and deleted flags, and then just return the beginning address of that array. The store routine takes a hash table, like the one returned by init. It takes a key, which is a string, and it takes a value, which is this struct data. It's a pointer to a struct data. Okay, this is important. The type def value with an uppercase V where do I have it? Is a pointer to struct data star. It's a type def to struct data star. So when I say that you're passing a value, this last argument on store, that's a pointer to a struct data. So somewhere you're going to have an actual struct data with these three fields, the reason the person's famous, birth, and death, and you're passing the address of that to your store routine. Okay? If you get that wrong, you'll segfault it really quickly and you'll figure it out.
So we won't actually call that store routine until we've collected the data from the user, and then store that into like a temp and then pass that to.
Exactly. You're going to have collect data from the user, you're going to make a struct node, you're going to fill in the fields of, struct data, and then you're going to call store. Give it the address of that, give it the key, which is a string, give it the table, which is a pointer to, a hash entry, and it will try to store it in the table. And it will return one of three things. 1 if it succeeds, 0 if the table is full, and -1 if that key is already in the table. So don't insert the same key twice, don't replace, just say it's already in there, you spit back a -1. All right, and we've talked about the way to do that, but here's a synopsis of how you do this. Set your attempt number to 1, take your key, hash it with probe equal to that attempt number, check that hash entry in the table and see if it's in use. If it's not in use, store the key, store the value and key in that entry of the table, clear the in use, set the in use, clear deleted, and return a 1. Otherwise, bump up your attempt number, rehash, and keep going. And after you've done this hash size times without success, you can say the table is full and return a 0. And this note here that I had in red on the asterisk yesterday, when you store the key and the value, you have to do some work, right? Remember that the key and values are pointers to strings and struct datas. So you're going to need to allocate space, you're going to need to copy fields for the struct data. And again, if you don't do that right, you'll either get segfaults or you'll store your data and it won't be there when you look, and you'll figure it out. All right, fetch is the opposite of store. So you go in with a hash table, and you go in with a key, and it returns a value. Again, a pointer to a struct data. If it doesn't find the key in the table, it returns null. Otherwise, it returns the address of this struct data, and then you can pull off the fields and print over to whatever you want to do. So algorithm is similar to the store algorithm. Set an attempt number to 1, hash your key with that attempt number, and check that hash entry in the table. So if your table is called table, table bracket, whatever the hash function returned, dot in use. Okay? If in use is 1, and the key that's stored matches the key that you're searching for, you have found your entry, so return the value from that array. And you can just return the pointer directly, you don't have to copy anything. If in use is 0 and deleted is 0, then you did not find the key and return a 0. Otherwise, in use is 1 and it didn't match, or in use is 0 but deleted is 1. And in either case, you need to increment the attempt number, go back and repeat those 3 steps. And if you do all that 101 times, you know that the key is not found and return is 0. Still with me? All right, delete, almost the same as fetch. So give it a table, give it a key, and it will try to delete that from the table. If it succeeds, it returns a 1. If not, it returns a 0, which means it didn't find the key. So set the attempt to 1, hash the key with that attempt for the probe number. If it's in use and the keys match, that's the thing to delete. So clear the in use, set the deleted, and return success. If it's not in use and deleted is 0, the key is not found, return 0. Otherwise, you have to probe again. So increment your attempt number and repeat those 3 steps. And if you do that 101 times without success, then the key is not in the table. And your table is probably full. All right, release. This is everyone's favorite. So this frees all the allocated memory used by your hash table. You call this at the very end of your code to release everything. You give it a pointer to your hash table. Right, hash is a struct hash entry star, so it's the address of the array that stores your hash. And it doesn't return anything. So what do you have to clear? You have to clear, look at what a hash entry is. So your hash entry has a key. This is a car star that you're going to dynamically allocate, so you need to free that space. This is a struct data star. So you allocated space for a struct data, so you need to free that. But before you free that struct data, you also need to free one field in that struct data, which is the reason why they're famous, the legend. So that's also a car star that has to be dynamically allocated. So you have to free the legend, and then you can free the actual struct data. And you do that for each hash entry that has a key and a data value. And then when you're done, you free the entire array of 101 hash entries that was created when you called init. So you got a lot of stuff to free. All right, so that's what release does. I will talk about iterators shortly. So additional info, so I'm going to give you a hash.h and I'm going to give you a database.c. That's the final main program. There's a directory where you can find those, or you can pull them from the website, but they're easier to take from the Linux server. So that should be readable by everybody, HomeNIC, public HTML, share PA3. You'll find those 2 files. All right, you'll want to use hash.h in the beginning of any file that uses your hash functions. Okay, it'll include the prototypes, it includes hash size, it defines what a struct data is, it sets up the type defs and so on and so forth. If you want to add additional things to that, feel free. That's fine. All right, you can work on groups. No predefined limit on the length of keys or the reason why someone is famous. And I will test your code with some million-character descriptions of why this person is famous. So don't hardwire a length, because it's not going to be long enough. And if you make everything 1,000,000, it's going to run out of memory. dynamically allocate space, okay? You can put this all in one big file. You can make totally separate files for each function. It's totally up to you how you organize this. You need to include a make file, and your make file should build the executable version of database.c. So when you finally turn in, when you turn in your final version of the code, have it build this main program that I've given you. But again, do your own main programs on the way there. Make sure you're using the hash algorithms we've talked about, right? You can delete by just starting at the beginning and just iterate through your array until you find your key and then set the flags, but that will cost you a lot of points. Okay, you want to be using the hash algorithm where you actually take the key and you hash it and you check that index, and if there's collision, you increase the probe and hash again. You got to be doing that, otherwise there's no point. You're not actually doing a hash, you're just doing an array. Okay, so the point is to make this efficient by using those hash algorithms. So testing, right? Obviously, you really want to develop this in steps. And don't be afraid to simplify things. So you're dynamically allocating space for the key and you're dynamically allocating space for the legend. But if you don't want to mess with that today, don't. Make them fixed length. Just make them 32 characters. And go back later and put in the dynamic memory for those. Right? If you want to work on your insert routine and your fetch routine, simplify away all those other details. If you want to work with a simpler structure than a struct data, make a simpler structure. Right? Make your own definition of what a value is. Have it just point to a character. And now your key is a string, your data is a string. You can develop store, you can develop fetch, you can develop delete, you can develop print. And once you got that done, now go back and change the structure to make it more general, right? So you've got 2 weeks, and there's enough in here that you could spend a little bit of time every day for the next 2 weeks working towards the final program. And that's not a bad way to do it, right? Or every other day or whatever your schedule permits. But leave yourself enough time to make sure that you're not, in a mad panic of blurry fingers on keyboards a few days before it's due. So here's a sample main program that you might use to do this development. So standard include stdio, include hash.h. And here I'm prototyping my hash function. You're not going to do that normally because that's not part of the interface. But I want to see what my hash function is doing. So I'm prototyping my actual internal hash code from ODP 10. And my main program is doing the following. It defines table to be a hash. It calls a niche. And if you run this in GDB, you can stop right here and look at your table and see exactly what's going on. And we'll do this in a few minutes. Now I've got a variable v, which is a struct data. I set the birth field to 1900, the def to 0. I set the legend to testing, and I do that just by saying it equals, quote, testing. So I'm hardwiring that. And now I say store. Store, here's the hash table. Here's the key I want to store, and I'm just using double quotes test key, and I pass it the address of my struct data. And I'm also printing out what the hash function will return for test key on probe attempt 1. Since my table's empty, it should find space there. And now, if I run this in GDB, I'm going to stop right here. And I'm going to go into my array, and I'm going to look at that element, 59, whatever it returns. And I'm going to see, did it store my key? Did it store my struct data? And I'm going to make sure that what I see in there makes sense. And then maybe once that's working, I've finished my store and I write my fetch, I'll just go ahead and do a simple fetch. So value result equals fetch, and I'll try to fetch something off the test key. And in GDB, I can look at the value of result and see if it is populated with the fields that I stored. And then I can try to fetch bad key, and hopefully it doesn't segfault, and hopefully if I look at result, it's equal to null, and so on. So this is really, really a good place to do development in steps, right? Because if you write all your code at once and you make one mistake over here, you're going to repeat that mistake a lot of places. And you're going to end up doing a whole lot more work trying to correct those issues. All right, once your functions work perfectly, you can play with database.c, blah, blah, blah. All right, submission, turn in a tar or a TGZ file, including all the source code, the include files in your make file, and it should produce an executable version of database.c. Now you're going to ask that only one person per group submit that file, but make sure the names of both people are on the top of each file. Okay? If I end up grading like some group's program twice, I'll be upset. I'll try not to do that though. So let's talk about iterators.
I do have one more question.
Yeah.
So, down in the notes section, you say there's no predefined limit on the length of the keys. But then in your do add subroutine, your F gets is only taking the first 4,000 characters.
What do add subroutine?
In database.
Oh, that's just a sample main program.
Okay,
I might change that to 4 million.
okay, all right. I didn't know if this was going to be the actual main program that it's going to be using.
It's one of them.
Okay.
But I'll have some edge case programs also that insert and delete 1,000,000 times to make sure you're actually deleting and freeing. And I'll have another one that inserts, 1,000 character string to fill up the array. And I'll have something that inserts, a few million character strings and so on and so forth. All right, so let me talk about iterators. So an iterator is a general concept. It's the idea that you want to pull things out of a data structure, but there's not a natural order associated with it. For example, with an array, if you want to read all the elements in an array, you can just make a for loop for I = 0 to whatever and just print out each element of the array. With a linked list, you can start with the first node and just follow the links and get to every node. But with a hash table, we don't have an easy way to pull data out because we don't know what the keys are. Right? And because our keys aren't just simple integers starting from 0 and going to something, our keys are Azad and Nick and CJ, how do we know what to query the database with? How do we know what to send to fetch in order to get back all the information in there? So the idea of an iterator is, in this case, it's something that's going to give us the keys that are in the table one at a time. And we do a pair of function calls. We call init iterator. It doesn't take any arguments, it doesn't return anything, but it prepares the system to hand us keys each time that we say next key. So the first time I call next key and I give it the hash table, it should give me back a key from the table. The next time I call next key, it should give me a different key. And the next time it should give me a different key, and each time I call it, it should give me back a different key that's in the hash table. And after it's returned all the keys, if I call next key once more, it should return null. So if I want to print the contents of my entire hash, I can say call init iterator, and then I can say while key = next key is not null, fetch the data stored at key, print out that value, and I can just keep looping until it returns null. And we'll meet iterators in lots of different applications. It's a useful way to do input. When you're trying to read input and parse it, you can say, give me the next token, and break things up like that. And we'll encounter these in Java a bunch of places. So you'll want to write one of these iterators, and that'll be used by the print function. So, yeah?
That we do run through just like a normal array, like we don't have any other.
That one you're just going to have to go through the array, right? But that's, under the hood, right? So your main program doesn't want to have to go through the array for I = 1 to hash size, right? Because your main program doesn't know anything about that. So the iterator does that dirty work and just hands you keys. And now if you implement this in some different way, the iterator still works. So yeah, let's take a look at
in the event of modification.
Yeah.
Such as ours.
Yeah, there's some issues with Java's iterators.
How should ours handle a modification, Jerry?
Like if something changes while you're iterating, just assume it won't happen. In reality, it's a hard thing to do in general, actually. Like if you delete the next thing that's supposed to come up, just have it do whatever it does. And it will not make changes to your database while I'm iterating. All right, so, we got 1 minute. Take a look at this at home. But basically, I've got a main program. I've got a bunch of helper programs that I've written in here. You don't need to understand any of this, right? All you need to do is link this together with your hash routines, and it should work. But I'm doing things like, for example, when I want to add somebody, I do a bunch of fgets to read in the information that I want to save. I throw all of that into a structure, which I call new, and then I say store table, comma, key, comma, address, new. And if it returns 0, I say we're out of space. If it returns -1, I say it's already in the table. Otherwise, I say success, and so on and so forth. So take a look at that. We'll go through this on Monday, and I'll also pop us into GDB, and we'll run through that little test program that's in the assignment and see sort of what these things look like as they're being built. And then we'll go on to the trees, hopefully in the middle of next week. All right, see you in club meeting if you're coming. Otherwise, have a good weekend. I'll see you next week.